Hey everybody, it's Throwback Monday. It's a throwback to when we had COVID. Welcome back, and thank you for joining me in this way today and for your flexibility. What a wild time of life this is. I want to open this class with a question, and you already know what the question is. And yeah, I'm still going to ask it. What did we do last time? Take a minute, think about it, write it down, don't use your notes, and I'm going to use this minute to go get some eggnog. It's good nog. Yeah, I'm okay. In an effort to make this room look clean, I just shoved everything over to there. Makes it a little difficult to exit the room. I wasn't planning on that. So what did we do last time? Well, we've been talking about Riemann sums, and the idea here was cramming rectangles underneath a curve in order to approximate area. Now, the original version of our Riemann sums was deciding how many intervals to break it down into, choosing how to send rectangles up to the curve, and then we just do that over and over again for however many times needs to be done, and we can send it up by the left endpoint, or the right endpoint, or the midpoint, or a random point if you're into that kind of thing, but don't be into that kind of thing. And we just did that for all of them. In this case, n was 8, so we had to do it 8 times, going up by the midpoint in this case, finding the area of each rectangle, which is base times height. The height is the value of the function at wherever that point is that we choose to send things up, right? In this case, we went by midpoint, so we find the midpoint of each subinterval and send that up to the curve. That determines the height of the rectangle. Widths were always the same. That was just the delta x that we've got going on. So I find the areas of all of those rectangles and I add them all up, and that gives me an approximation of the area. In this case, 25.25. Actual area underneath this curve is 25.33, so that's not bad. But then we went one step further and said, hey, the whole goal of these Riemann sums is to approximate area, but the more rectangles I cram under the curve, the better that approximation gets to be. So if I cram it up to 100 rectangles, that's really great, but it's still not perfect. On the other hand, breaking the glass here and letting the number of rectangles go to infinity, that would give me the actual legit area under the curve. That's what I'm after. So that brought us to the next part of our plan, setting up an arbitrary Riemann sum that would allow us to find the actual area under the curve. And I gave a couple examples that I want to go through again here. The first one both classes made it through, so I'll kind of speed through this one. Looking for the definite integral of x squared plus 1 from 0 to 4, that is the area under the curve. And our tactic here was, first of all, choose a method. Choose whether you want to go by left endpoints, right endpoints, midpoint, or what have you. I mentioned in class that from here on out, I'm going by right endpoints. That's where it's at, yo. Second, set up a Riemann sum for an arbitrary number of subintervals. A Riemann sum is just adding up the sum of the areas of all of those rectangles. We don't know how many there are, there's n of them. We're picking some point in each subinterval that we are running through the function and sending it up to the curve to find the height of that rectangle, and then multiplying it by the width of that rectangle, the delta x sub I. Now, we've always done delta x sub I to just be delta x. I'm not letting the widths of my rectangles change. That's just too much. There's no need for that kind of business. And the way that we've always found it was with b minus a over n, the length of the interval divided by the number of rectangles that need to be crammed into it. In our case, that's 4 minus 0 over n, or 4 over n. That was our delta x. As for the c sub I, well, we're going by right endpoints, and the line of reasoning to have here was that however many my values of n are, that determines my delta x value, the width of each rectangle. And each c sub I is coming by just taking the starting point and then adding the width of each rectangle over and over again until I get to the next one that I need. If n was 8, delta x would be 1/2, and I'd be starting at 0 and then adding 1/2 over and over again. So the formula for my c sub I would be the 0 I'm starting at plus 1/2 times I. Every time I goes up, I move over by another 1/2. In general then, we'll start at A and we'll add delta x times I every time I goes up by 1 to add the next rectangle's area. The point that I'm going to run through the function is going to just start at that a value and then add I instances of the width of each rectangle. Now we just found a moment ago that that width of that rectangle is 4 over n. That was the delta x that we went with. That's what I'm going to be running through the function. Of course, I don't need to say 0 plus anything, that's a waste of everyone's time. And also I can pull constants out of the sum. Only I is changing, n is not. That makes it a constant that I can pull out. From here I can simplify this since I know what the function is. The function was x squared plus 1. So if I take this and run it through that, I get that thing squared plus 1. I should really have parentheses around all this, by the way, since it's better and correct to do so. But I'll get there in a moment. If you actually square this out, you get 4 squared is 16 over n squared is n squared times I squared is I squared, plus that extra 1. That's what I'm adding over and over again. And here I can start using my summation rules to clean this up a little bit. I'm allowed to split summations up over a sum. And I know what this summation is supposed to be. That's not the one I wanted. I know what this summation is supposed to be. Adding 1 to itself n times gives me just n. And I can pull this constant out of the summation. Now that I split up my summations, I have the freedom to do that. And now once again, this summation here is going to be one that I actually know. After I clean up a little bit more, distribute my 4 over n to both pieces, then I can focus on this last weird summation. We'd studied 4 of them, 1, I squared, and I cubed, and so I know the values of all of those. I can replace that with the expression that only involves n, no i's. Make cancellations as needed. You can't see me, but I actually just flinched when that happened. I totally forgot about that. Totally forgot about that little effect. Make some cancellations with n's and 64 over 6. I didn't have to tell you that either. You could have just not known that I'm a wuss. But here we are. Cleanup is needed, expand where I can, and then put together a fraction where now I have an expression that's just n. If you give me the number of n, I can tell you the area under the curve if you put n rectangles under that, the Riemann sum that I get from n rectangles, whether I put 4 rectangles or 8 rectangles or 100 billion rectangles, I can tell you what I get. So the natural next step is to take a limit. I want to know what happens with the area with this as n goes to infinity, as we crank up the rectangles and have that go bigger and bigger and bigger, so that I can get the actual value of the area. Actual value here, 76/3, which is approximately 25.333 as promised. And that is our solution. And we had this theorem that said that this always works, that if you want to get the area under the curve, you can do so with a Riemann sum. Now for some of you, that's where we left off. For the second class, for my 9:30, you guys did the next example, so if you want to skip this part, you're welcome to do so. But I do want to go through that second example of finding the exact area with a Riemann sum one more time, especially for those who haven't seen it yet. So let's do that. Let's evaluate this definite integral using Riemann sums. Our process here is the same as before. I want to start by figuring out what that delta x should be. I'm going from 1 to 11. I need to find the keyboard shortcut for that. Laser pointer. It's probably Control L, right? I'm not going to try. 1 to 11. Okay, that's the width of my interval then, right? Is 11 minus 1, which is 10. And I'm dividing that by the unknown value of n because I'm keeping that arbitrary. I don't know what n is. It's going to be changing. That means my delta x is 10 over n. Great. Now what? Well, now I need to set up that Riemann sum and go ahead and I'll go ahead and write out the whole thing right now. This is just incorporating everything. I've got f of my c sub I, my right endpoint, is going to be starting at the value of 1, and then adding I times delta x. That's all going into the function. That all gets multiplied by my delta x, and after I take the sum, I take the limit. So I'm just writing all of it in one big line right now. Okay, well I know delta x, that's 10 over n. So I get I times 10 over n on the inside, and a 10 over n on the outside. I can clean this up a little bit. Yeah, you know, that's probably not what you had in mind when I said clean it up, but it's, you know, we're making progress toward our destination. What happened here? Okay, deep breath. This 10 over n here is a constant, and got moved out to the outside of my summation. I will always be able to do that. That delta x is always going to be a constant. It's just going to be something over n. So I can just plan for that to just come right on out. As for the rest of this, well, this all has to get plugged into the function, right? My function being x squared minus 5x plus 2. So everywhere I see x, I have to put 1 plus 10i over n. Yeah, that's a good time. A little bit more unfortunate than the previous example, because in the previous one I had a 0 here, which meant when I squared things it wasn't so horrible. But now I am gonna have to like foil this out and do, you know, square the first, multiply the two together and double it, and square the last and all that jazz. It's tedious, but it's not hard. And I'd rather have a plan that I hate than no plan at all. Squaring the first, 1 squared is 1. Multiply the two together and double it, that's 1 times 10i over n, doubled is 20i over n, plus square the last gives me 100i squared over n squared. Here distributing my negative 5 gives me a minus 5, and then minus 50i over n, and then plus 2 is along for the ride. I'm going to combine my like terms, which is a few. 100i squared over n squared is the only term that looks like that, but I do get I over n terms. 20i over n minus 50i over n is negative 30i over n. And then I get 1 plus 2 is 3, minus 5 is negative 2. So I've got all of this business here rearing and ready to go. From here, it's a matter of splitting up my summation and then using the rules that I know. Splitting up the summation over its 3 terms lets me invoke the 3 summations that I'm going to know something about. From my first term, I'm able to pull out that 100 over n squared, leaving I squared on the inside. From my second term, I can pull out this negative 30 over n, leaving just I on the inside. And as for this minus 2, well, I decided to write it as pulling the 2 out and leaving 1 on the inside, to highlight that I actually do know this summation. And I do. I know all 3 of these. The rule for I squared is hideous, but it is what it is. We know it for I, we know it for 1, we know it for all of them. I'm going to go ahead and distribute my 10 over n, though. That's going to give me 1000 over n cubed when it multiplies by this one, 300 over n squared when it multiplies by this one, and 20 over n when it multiplies by this one. Getting a little lag on my laser pointer, so I'm trying to like move it in advance and see where it goes. It's kind of a lot of fun. I like to think of my problems as fun problems. Okay, now I know what each of these summations is. If you take the sum as I goes from 1 to n of I squared, you get this whole business. The sum as I goes from 1 to n of I is just this, this good one. And the sum as I goes from 1 to n of 1 is just n. So that one we know. Now it's about cleaning up. In every summation, there's an n, and I'm almost always going to be able to like cancel it with something. Here, this n is going to cancel with one of my n cubeds. This n is going to cancel with one of my n squareds, and this n will just straight up cancel with that n, so it's a great day. That's 1, that's 2, and that's 3. When you cancel all of those, things get a little bit better. I've still got 1,000, which is something to look forward to. But I like this a lot because now, since I have to multiply, these 2 terms together, multiplying 2 of them together is a lot better than multiplying 3 together. I think anyone would agree. So if you distribute this, then you get this business. And this is phenomenal because I don't even have to wait for you to write this down. You can just pause this video whenever you need. It's incredible. From here we're at a point where I've got an expression that's entirely in terms of n, and I am safe to take a limit. So, with my first term that I'm going to get here, and I just realized that my second class didn't actually finish this question, so hopefully you stuck it out to here. Or welcome back. Maybe you skipped ahead to this moment, in which case it's great to see you. Here I've got, taking the limit as n goes to infinity, but I've got n cubed on the bottom and the top. Those are my highest degree on the bottom is the same as the top. So here I'm just going to get the ratio of those leading coefficients, 1000 over 3. Same deal over here. I've got n is my biggest on top and the bottom, so I'll get 150 over 1, but don't forget that it's negative. And then 20, the negative 20 doesn't actually have any variables in it, so that's just going to remain as a negative 20. Meaning this is 1000 over 3 minus 150 minus 20, which is 490 thirds, which is about 163.33. My animation timing is a little off, but here we are nevertheless. The process looks pretty much like that every time. We figure out what our delta x is, we set up the general Riemann sum, we work it out, which is often unfortunate, but it's not too bad. It's what I call a Netflix task. It's the kind of thing that I can do while watching Netflix, because it doesn't require a whole lot of thought, it just requires a little bit of time. Granted, it'll take 3 times as long if I try to do it while I'm watching Netflix, plus the time it takes for me to actually pick something to watch on Netflix, but that's not going to stop me from doing it. go ahead and practice this. I've got to try it with a buddy here. I know that you don't actually have a buddy near you, probably, who knows calculus, unless you're, rooming with someone who's taking this course or has already taken this course, in which case, if you're able to round them up and make this a buddy moment, then go for it. But otherwise, just go ahead and work it out on your own, and pause the video here so that you can take a moment to practice this, and I'll put up a solution in a moment. Here's what I get when I do this from my setup and onward. Conveniently, the left endpoint is 0. I'm going to try Control L. Oh my gosh, it worked. That was phenomenal. Okay, so 0 is my left endpoint. My delta n, 3 over n, so I get 3i over n, and then a 3 over n here. 3 over n can be pulled out. Everything is just x cubed, so it just goes into the cube. When I cube it, I can pull out a 27 over n cubed, making this 81 over n to the 4th. So I have just an I cubed. This was our rule for the I cubed, which you'll need to, expand a little bit and pull things out there. It actually cleans up pretty nice, all things considered. And when you take the limit as n goes to infinity, you get 81 over 4, which is 20.5. That is the exact area under the curve. That's all I've got for that section, but I do want to start the next section. It's going to take us into some really important pieces. So let's get right into it. This is section 6.3 on a result that sounded like it could be kind of important, so I felt like I should cover it, called the fundamental theorem of calculus. I want to start this section by introducing you to a kind of a new sort of function, so take a look at this thing with me. Let's say that we take a function, I'll call it f of t equals 3t, and I'm going to make another function that uses that in kind of a neat way. It's okay, it's going to be okay. I'm right here. I'm right here. Capital F of x is equal to the integral from 0 to x of 3t dt. So this is a function where you give me a value of x, and then I work out the definite integral from 0 to the x that you told me of 3t with respect to t. So in other words, it's the area under the curve between 0 and whatever number that you say. This function actually doesn't really have like an official mathy sounding name, so I'm going to call it the current area to here function. It seems like a good one, or CAF for short. Yeah, the original title was going to be current area to here excluding the external regions. But I didn't like the acronym. The current area to here function. So essentially, here's how it works. If you want to find f of 2, for example, f of 2 is the integral, the definite integral from 0 to 2 of 3t dt. And here's the graph of 3t. It's just the linear function of 3 times t. And then our function finds the area under that curve between 0 and 2. That's what a definite integral is, right? It's the area under the curve between those values. You give me 2, I find the area between 0 and 2, and in this case, well, it's all a triangle, right? So it's just base times height times 1/2, so that's 2 times 6 times 1/2, which is 6. Easy peasy, lemon squeezy. Let's try another one here. Suppose you want f of 7. Well, f of 7 is the definite integral from 0 to 7. That's where the input goes, right? Everywhere in my function named capital F, I put 7 everywhere I see x, and, well, it's up there at the top of that integral. So we get 0 to 7 of 3t dt. That's the area under the curve between 0 and 7. Well, again, that's just 1/2 base times height. That's 1/2 times 7 times 21, which is 147 over 2, which is a lot. And Yeah. So that's the idea of the function, right? It's finding the area under the curve between 0 and x. So this function looks kind of intimidating, and rightly so. It's a function that has an integral in the function, where I'd have to do a different integral every time I wanted to evaluate something with the function, which is intimidating. I don't really want to do like a Riemann sum every time, right? Because here it's linear, right? Easy peasy lemon squeezy. But you make that like a parabola or something, that's going to be difficult, lemon difficult, right? I'm not looking forward to having to do a different Riemann sum every single time I want to find the area underneath it. So a few things about this that will make this a little bit better as we talk it through. First, I want to mention that this is a function that's actually used. And second, I want to put your mind at ease that no, we're not going to be having to do a Riemann sum every single time I want to work something out, for the same reason that I don't have to take a limit definition every time I find a derivative. Yeah, it sucks at first, but that's what we do in calculus. We take things that suck, and we make them better. First thing about this is we can generalize this function. I mean, before we were doing it with f of t equals 3t, but you could do this with any f of t, right? I could make any choice that I want. I could have my starting value be any choice of any constant a. Ours went from 0 to x, but you could do, in general, a to x of f of t dt, and that would be totally fine. So if you wanted to make something like from -3 to x of t squared dt, well, that's totally fine. It would just represent the area under the curve between -3 and x underneath the curve t squared. Totally legit. Second, we actually know a little structure here. Not a whole lot, but the pieces we know are actually surprisingly valuable. Here's kind of an interesting thought here, right? Suppose I wanted to find the area under the curve of f of t between a and a. What would that be? Yeah, that's right. I'm just going to ask questions and then pause, and you can answer them out loud like you're watching Dora the Explorer. It's great. Yeah, that's right, everyone. 0. I can't have any area under the curve beneath a single point, right? If I go from A to A, I haven't gone anywhere. You could think of it like this, right? Your delta x for each one, if you did a Riemann sum, would be a minus a over n, which is 0 every time. And you'd be adding up a slew of zeros when you did your Riemann sum. But yeah, that means that since that area is 0, that no matter what my capital F is, no matter what f of t you choose, no matter what a is your starting point, we'll always have that relationship that capital F of a is equal to 0. That's really kind of one of the only, basic pieces of structure that we get. We get some major pieces of structure that we'll see in a moment, but this little gem is surprisingly useful. Speaking of being surprisingly useful, number 3, this function is surprisingly useful. You might be wondering when I would ever actually care about a function like this that finds the area under the curve so far. Unfortunately, for the sake of time, I had to cut this from the video because it's already just extraordinarily long. But I did record all of these examples, so if you want to see them, just let me know. Number 4. This function has a connection to anti-differentiation. This is really the meat and potatoes of this section, because this connection comes in the form of a theorem called the fundamental theorem of calculus. Part 1. Let f be continuous on the closed interval from a to b, and let capital F of x equal the definite integral from a to x of f of t dt, our cath function from earlier. Then capital F is continuous on the closed interval from a to b, differentiable on the open interval from a to b, and here's the part that we actually care about, capital F prime of x is equal to little f of x. That the derivative of capital F of x is the inside of that definite integral the little f of x. In other words, if you want to take the derivative of this definite integral function, that the derivative is just what's inside, essentially, suggesting that there's a relationship between definite integration and indefinite integration, a connection between the definite integral and an antiderivative, that they undo each other. I need you to understand how big this is. Like, this is enormous. Like, you look at this theorem and you're like, this is literally all Greek to me, and that's cool. We're going to explain it in a moment. But this is an enormously huge and wonderful theorem, because this theorem essentially creates the connection between differentiation, anti-differentiation, and area, between the indefinite integral and the definite integral. It tells us that essentially integration, or definite integration, finding the area under the curve, can be found with an antiderivative. Let me show you this example to show you the power of this theorem. Here's the example. Find the derivative of capital F of x equals the integral from 0 to 2, the integral from 2 to x of 4t cubed plus the sine of t dt. Now, finding the derivative is not even going to be the most interesting part of this problem. But have a look at this. According to the fundamental theorem of calculus, if I want the derivative of f of x, if I want capital F prime of x, the fundamental theorem of calculus says that this derivative is just this function in here. I'm swapping out t with x, and that's the way that the theorem lays it out, but here it's just the name of the variable, right? I can swap out for whatever we want. And so here, I could say that the derivative of f is 4x cubed plus the sine of x. That's what the fundamental theorem of calculus says. If you've got this wild function here with an indefinite integral, any function that's in this form, that we know its derivative is just the inside. Now this is huge, right? Because this means that integration, definite integration, and differentiation undo each other, since taking the derivative of this essentially just gives me what's inside. Now, that also means that I can actually know what this capital F of x is as a normal looking kind of function. This capital F of x apparently has a format that doesn't look as hideous as this, which is great news, because I don't want to work with this. I don't know how to do Riemann sums of things with sine in them. I'm not excited about that. I don't even want to know. I'm not even curious. Okay, I'm a little bit curious, but I don't need to know. I don't care to know. I kind of care to know. This f prime of x being equal to this means that I could just take an antiderivative of both sides, an indefinite integral with respect to x, and figure out exactly what the function capital F is supposed to be. That's just coming from, well, the power rule on the first term and our Math's Most Wanted board on the second tells me that capital F of x is the antiderivative, x to the fourth minus cosine of x plus c. I can even know what that plus c is, because I know that f of 2 has to be equal to 0. That was one of our rules. That was that one piece of structure that we knew from earlier, that if I go from 2 to 2, the area is 0, so f of 2 must be equal to 0. And that's actually enough information for me to figure out what that value of capital C has to be. If f of 2 is 0, then I'll just plug in 2 everywhere I see x. I get 2 to the fourth minus the cosine of 2 plus c is apparently equal to 0, and by moving everything over to the other side, I get the cosine of 2 minus 16. That's the value of c, which means my capital F of x, plugging this business into my c value, means that capital F of x is this. Instead of having to write that horrible format that we were given, that the original capital F of x was the integral from 2 to x of blah blah blah, I don't need that anymore. I can find the area under the curve between 2 and any value of x that you give me by just plugging it into this. Instead of the format here that's in black, I can use the format in purple. So if I wanted to find the area under the function between 2 and 5, I don't have to do any business with this of indefinite integral from 2 to 5 of blah blah blah. According to the fundamental theorem of calculus, I'm able to write this f of x function like this and plug 5 into this. I'll get, 625 minus the cosine. I'm not thrilled about all these values, but I have a calculator that can do it for me. And when I do so, I get an approximate value of 608.3 blah blah blah-ish, right? No Riemann sum required. No need for a summation, no need for anything other than an antiderivative. Holy smokes, I am so much happier doing this than a Riemann sum. So this is huge, right? Instead of having to take a Riemann sum to find the area under a curve, I can just find an antiderivative? Yes please. I am all about that life. Shoot, we're pros at derivatives, right? How much harder can antiderivatives be? Sorry, I couldn't. They're way harder, but they're not impossible, and we get techniques for them, and they end up kind of being a really interesting puzzle sometimes. They may not have the straightforwardness of derivatives, but we have effective techniques for finding them, and I don't necessarily have effective techniques for Riemann sums. If you give me a summation inside of a sine, I don't know what to do with that. Inside of a logarithm, an exponential, any trig function, I mean, shoot it, unless you put it inside of a polynomial that's like cubic or less, I'm toast, right? But I can take antiderivatives of a lot of different things. So to have this connection between antidifferentiation and integration is so powerful. And it gets even better. Number 5, this function makes integration a breeze. We still have kind of that one slight limitation where it looks like I'd always have to start at whatever the lower limit of the integral is. But there's a part 2 of the fundamental theorem of calculus that even takes that limitation away. Furthermore, if capital F is any antiderivative of f, then the definite integral from a to b of f of x dx can be written as capital F of b minus capital F of a. In other words, if you want to evaluate a definite integral, you don't even have to set up all of that business that we did before and invoke the fundamental theorem of calculus by writing a function, taking its derivative, and solving for c. I don't have to even do that. I mean, that was already way better than taking a Riemann sum, but even that is more than I need to do according to this part of the fundamental theorem. If you want to know the definite integral, the area underneath the curve between a and b, you just take an antiderivative of this little f. Now remember, the collection of all antiderivatives is our indefinite integral. That gives me that plus c. But the fundamental theorem here says I can use any one of them. I can pick any function that I want. I might as well pick the one where c is 0. That's the easiest one to work with. I can take that antiderivative and just plug in b and plug in a and take the difference. And that is enough to give me the area under the curve. What a phenomenal theorem this is. Let me show you some examples. Here, let's evaluate this definite integral from 0 to 3 of x squared minus 6x plus 4. Okay, so according to the fundamental theorem of calculus, part 2, I can just take an antiderivative of this expression and just plug in the endpoints. Well, the antiderivative of this expression is a breeze because it's all just the reverse power rule. So that'll just be 1/3 x cubed minus 3x squared plus 4x. And then here's the way that I'm going to write it, by the way. I'm going to use brackets. I like to do brackets on the outside around my whole expression. And I put a 0 down here and a 3 up here. And that represents this calculation that the fundamental theorem is talking about, of taking the 3 and plugging it into all of my x's, and then subtracting from that, taking the 0 and plugging it into all of my x's. I've also seen people write this a little bit differently. It's not uncommon. I don't think the red's going to show up very well. It's not uncommon to write something like 1/3 x cubed minus 3x squared. This is why I do everything in PowerPoint. I mean, I am doing this in PowerPoint, I guess, but not like this normally. I see people it's not uncommon to do like just a tall vertical line and put like a 0 and a 3 like that. That tall vertical line means the same thing. If you look in your textbook, I think they probably write it that way. A lot of people write it that way. A lot of people do the brackets too, and I like the brackets because I feel like it also highlights, what expression exactly is all this going into in case there's more than one. But now when I plug this in, what this means then is I'm plugging in a 3 everywhere I see x, and I'm just evaluating that, just plugging in 3 for all my x's and seeing what I get, and then plugging in 0 for all of my x's and seeing what I get, and then I just subtract the 2. According to the fundamental theorem, that's enough to know the area under the curve, which here when you plug in this 3's here, you get 9, you get 27, you get 12. All of these are just 0, so those all just go away. And 9 minus 27 plus 12 is -6. -6, I get a negative number. So the area under the curve is a negative number. Well, that seems to suggest that my curve spends more time below the x-axis than it does above the x-axis, which is in fact the case. Forgot about that part. Yeah, it is actually below the x-axis more than it is above it. And so remember that our definition of a definite integral has this, down here count as like negative area, which makes a lot of sense with our Riemann sums, because when I take parts of my sub, intervals here, and I multiply them by the value of the function, well, that's going to be a negative number, so all of those rectangles would give me like a negative area that would get subtracted. Here's another one. Here we want to go from 3 to 8 of 5 over x minus 2 sine of x. And it's the same deal. To take this integral, I'll just take the antiderivative of both of my pieces. 5 over x is going to have an antiderivative of 5 times the natural log of x. Minus 2 sine of x, that's going to have an antiderivative of positive 2 cosine of x. And that just gets evaluated from 3 to 8. Don't worry about this little space here. In PowerPoint, PowerPoint doesn't automatically stretch out these brackets, and it's hard to get them to look the way I want. So I put a little invisible fraction right here so that it would think that I had really big things inside. You didn't need to know any of that, but I told you anyway. And now from here, it's just I plug in 8, I plug in 3. All of those are going to be values that I don't exactly know. But I can run them through my calculator for the natural log of 8, the cosine of 8, the natural log of 3, and the cosine of 3. And that gives me about 6.5931311190, as you might expect. So that's basically the big gist of this section, is that big result, that if I want to find the area under a curve, I can find a definite integral by taking an antiderivative and then just plugging those two values into it. I gotta try it with a buddy here, which you're welcome to try it on your own or with any buddies that you happen to scrounge up, and I'll show you the answer here in a moment. Here's what I get. I get that this antiderivative for the 4 over 1 plus x squared, if you pull that 4 out, you get 1 over 1 plus x squared, which has an antiderivative of arctangent, so we'll have 4 times that arctangent. And then the integral of 2e to the x is just 2e to the x. And those get evaluated between 0 and 1. For 1, the arctangent of 1 is pi over 4. That gets multiplied by the 4 to just give you pi. And then here we just get e to the first is e, times 2 is 2e. Plugging in 0, we get the arctangent of 0 is 0. And plugging in 0 here, I get e to the 0 is 1, times 2 is 2. But remember, all of that is being subtracted. So I'll get pi plus 2e minus 2. That is all I have for today. Thank you so much for joining me on this adventure. That feels like a strong word, but thanks for doing this with me, for your patience, and I'm sure you were just real sad to sleep in today. But thanks for joining me in this and watching this. I really appreciate it, and I look forward to seeing you all tomorrow. So have a very lovely day, and take care.